can I just give an intro? We are actually 10 minutes late.
Later.
So, yeah, so no issue.
Okay.
So, you can set your things are ready, like your presentations and all. So, meanwhile, I will just give your intro. You're just a small intro, sir. So, can I give your intro in meanwhile?
Yes, sir. Yes, sir. Yes. Yes.
Yeah, yeah. Thanks. Welcome everyone for today's sections. Today we have Dr. Periyasamy with our side to give a presentation on our biomedical thing. So I will just give an intro of Dr. Periyasamy, sir. Dr. R. Periyasamy received his BE in ECE with first class with distinction 2002, Kamraj University, Madurai. He began his career as a lecturer at SVCET, Puliyangudi. He completed his MTech in Biomedical Engineering 2007 from the Department of Applied Mechanics, IIT Madras. Following his post-graduation, he worked as a research officer at the Diabetic Food Clinic, Sundaram Medical Foundation, Chennai, where he gained in-depth clinical exposure to a diabetic food ulcer diagnostics and surgical management. In 2014, he earned his PhD in biomedical engineering from IIT Delhi. He's publishing over 15 international journal papers and 5 conference proceedings, with research featured in reputed journals like Journal of Engineering in Medicine, Journal of Medical Engineering and Technology, and International Journal of Diabetes in Developing Countries. Dr. Periyasamy's accolades include the Best Research Poster Award at the IEEE conference at IIT Kanpur and a Young Faculty Award in 2015 from Venus International Foundation, Chennai. He has also received travel grants from CSIR to present his research internationally. He served as an assistant professor in the Department of Biomedical Engineering at NIT Raipur from 2013 to 2018 before joining NIT Trichy in 2018. He is a life member of prestigious societies, including the Indian Society of Biomechanics, the Indian Science Congress Association, and the Biomedical Engineering Society of India. His current research interests span biomedical instrumentations, gait analysis, biosignal and image diagnostics, device development, near infrared spectrum, tissue oxygenation, and AI deep learning for disease diagnosis. He is also engaged in IoT-based system development. Dr. Periyasamy has led multiple funded projects, including 2 ongoing DST funded projects and on industry-sponsored initiatives, alongside 3 completed projects under SCRB and DST IDP. Publications in high-impact journals and significant contributions to biomedical research, Dr. Periyasamy continues to advance innovation in the healthcare technology. With this small intro, I welcome Dr. Periyasamy to this section. Sir, over to you, sir. You can continue. You can present your screen and you can continue, sir.
Thank you, sir. Thanks for nice introduction. So I'll share my screen.
Yeah.
Is it visible, sir?
Just wait. Yeah, it's visible.
Whether it is in first slide?
We are seeing it's in the okay. Machine learning based system for diagnosing pulmonary diseases, right? The first slide.
Yes. Yes.
Yeah, yeah. And
it's in
for
full screen mode.
No, it's not in the full screen. Yeah, now it's in full screen mode. Can you just change your screen? Change your slides?
Is it changing?
It's changing. Yeah, yeah. Outline of my talk. Yeah. Now it's that.
Okay.
Yeah.
Okay.
Good evening, Dr. Periyasamy. I'm the coordinator.
Yes, madam. Good evening, madam.
Yeah, I, along with my co-coordinator, Dr. Vaithiyanathan, would like to invite you from Department of Computer Science and Engineering and Department of ECE and IT Delhi. Sir, welcome you, sir. We are looking forward for your talk, sir.
Yes, madam. Thank you, madam.
Okay, sir. Okay.
Okay. So, good evening to one and all present here. So, first of all, I thank the coordinators and for giving me opportunity to deliver the talk on machine learning based system for diagnosing pulmonary disease. Whether my voice is audible, sir?
Yes, yes, perfect, perfect. Your voice as well as the screen both are perfect, sir.
Okay. Myself, I am Periyasamy. I am working as assistant professor in the Department of Instrument and Chemical Engineering from 2018 onwards. And today, my outline of my talk is I'll give brief introduction about lung sounds and pulmonary disease. What are the challenges to diagnose a pulmonary disease and what is objectives? And what are the AI-based systems for diagnosing various pulmonary diseases? In that, I will cover lung sound data acquisition by a standard protocol, how to denoise the lung sounds and feature extraction and evaluations, and classification of pulmonary disease using machine learning and deep learning algorithm. I'll cover three important work which was done by my scholar, machine learning based classification of pulmonary disease through lung sounds, recorded lung sounds, a robust approach to pulmonary disease classification via multifractal analysis of lung sounds. And finally, I'll give you a brief introduction about how the deep learning is used for detection of chronic and non-chronic pulmonary diseases, and conclusion, future perspective. So basically, my talk is related to respiratory disorder. Why to monitor respiratory disorder? We all know that according to WHO, respiratory disorders are very among top 10 global cause for death in 2019, and it's account for more than 88 million fatalities each year. If you see the right side graph, it shows clearly in 2020, the India recorded 10-year higher in the number of deaths caused by respiratory diseases. It shows in the graph. So it affects all the people, all the age group people, whether it is male or female. So if you see, millions of people are suffering from different pulmonary disease. It may be chronic COPD, or it may be asthma, or it may be pneumonia, or tuberculosis, lung cancers, bronchitis. So if you see, most prominent diseases, COPD is the third most cause of death globally occurring, and it is reported by WHO 3.2 million deaths annually happening, while 250 million individuals worldwide suffer from asthma. That is stated by the WHO in 2021 as well as 2023 also. If you see the graph in the pie chart, like you can see the most prominent, the green color is the COPD is 11.331%. So tuberculosis is 29.66%. So if you see the millions of people suffering from the different pulmonary disease. So that's a scenario is there. So that is why we want to monitor respiratory disease effect like non-invasively. It's a tool. Instead of using a spirometry, we can go for a simple tool to diagnose pulmonary diseases. So we know that how to monitor, like if you want to, with the help of lung sounds, basically when you oscillate with the help of stethoscope, the electronic stethoscope, you will get different sounds. It may be lung sounds, voice, or breathing, or cough sounds. With the help of, you can detect this respiratory disorder. But our research is focused on, with the help of electronic stethoscope, we are using a lung sounds for diagnosing different class, record the different class of sounds, and from that we are going to diagnose the pulmonary disorders. So existing method to detect the pulmonary disorder, like we all know that if you go to any hospitals, so if they'll first go for conventional method, they use a spirometry, that is a pulmonary function test. And if it is more severe, then go for chest X-ray, and then if it's more higher severe, then go for a computed tomography system. What is the limitation of the conventional method? If we see, all these methods have somewhere around some limitation is there. One is it's a complex diagnosis techniques, and when you go for a chest X-rays, frequent exposure to the radiation is harmful to the body. If you use a spirometry test to diagnose a pulmonary, detect the pulmonary disorder, there is a air leakage, like where you can't use it for like aged people. The air leakage will from the mouth while blowing during the spirometric test. It will create error in the measurements. So as well as when you go for a CT or like a pregnant woman or mental child cannot be applicable, not used. The computer tomography is not useful. So CT is costly diagnosing, and expertise is needed for this technique. So the field of pulmonary diagnosis is undergoing some significant transition from the conventional method to the AI, like artificial intelligence. So we are integrating this artificial intelligence with the imaging investigation for clinical decision making. That's what this transition is happening in the pulmonary diagnostic field. So basically, we are, as I mentioned in this slide, we are using a lung sounds for diagnose different pulmonary diseases. So we want to know what is normal lung sounds. So normal lung sounds, the nominal frequency range is 37 to 1 kilohertz. And you have vascular based on the area, like if you trachea area, if you oscillate with the electronic stethoscope, you tracheal sound, which has the dominant frequency range of 100 to 5K, and vascular, it's a low pitch sound, bronchial and bronchovascular. So each has different dominant frequency ranges. And if you can easily hear that the location is already mentioned here. So this is the vascular sound, and this is for the bronchial, and this is for the bronchovascular. And what is abnormal lung sound? It's a advantageous sounds where you can classify into continuous lung sound and discontinuous lung sounds. In continuous lung sounds, you have wheeze, roach, and discontinuous sounds have crackles. So wheeze, the dominant frequency is 400 hertz and duration is greater than 250 milliseconds. So where we can record it, you can see in the right hand side, there is a front and back chest portion is there. Central and lower air tracts, we show from that you can get the wheeze sounds. And roach, the dominant frequency is 200 hertz or less. The duration is greater than 250 milliseconds. And it's a low pitch where you can record in the larger airway tract, you can hear this roach sound. So crackles is a discontinuous lung sounds. In crackles, you have coarse crackles and fine crackles. And these locations, which we know that in roach, you can oscillate in the posterior upper and lower lung field. Crackles, you can in a posterior and anterior lower lung field. This, if you see the numbering is already mentioned, 6, 7 posterior means it is there in the figure. And wheeze, 3, 4 anterior and posterior middle lung field region where you can hear this wheeze sound. So these are abnormal lung sounds. And then we want to know what is auscultation. Listening to the lung sound with the stethoscope is a simple meaning of auscultations. So from the lung sound, you can be able to know the information about the pulmonary pathology. So it's a simple system where you can use a stethoscope to, by auscultation, you can determine what is the pathological conditions. So the recent studies, if you see the right hand figure where you can go have this stethoscope, simple stethoscope, where you have the chest piece and earpiece, you can hear this sound. With the help of, by oscillating the on the chest area, you can hear this sound. From that, you can determine the pathological conditions. But recent studies, what they use, the computerized procedure is more used instead of simple oscillation process. That's a new direction is applied. So in conventional auscultation, traditional stethoscope or e-stethoscope cannot be used for continuous monitoring because it is very sensitive in determining the respiratory problem and needs to be performed by a specialist. You can't use a specialist person can be used this electronic stethoscope or traditional stethoscope. So as in the study, what they find out, the lung auscultation with the help of stethoscope is sometimes it is questionable in accuracy. So what will happen? 60% only for they able to properly determine the pathologic conditions, and 80% of fellows properly able, because that's how that accuracy is going down. So in auscultation using conventional stethoscope, there are some points to be taken. Like this is due to clinical lack of experience and weak strength of signal and mixing of signal from the other organ. When you use a electronic stethoscope, traditional stethoscope to oscillate the particular area, there may be a mixing of signal from the other organs also. So these, if the down figure, if you see this, these are the auscultation points, and for different sounds can be detected. As I mentioned in the previous slide, wheeze sound, crackle sounds, roach sounds. From the sounds, you can diagnose the different pulmonary disease, whether it's COPD or asthma or pneumonia. So with the development of digital stethoscope, we can more accurate diagnosis can be done. And these digital stethoscope can be used for telehealth and clinical education also. But it is not widely used, this digital stethoscope, because it's inconvenience. And recently what has happened, wearable stethoscope is developed with the help of accelerometer or microphone for acquiring these sounds, speech, cough sound. But it is, what is the problem in wearable stethoscope? It is difficult to detect the acoustic signals due to characteristics of a vibration measurement based sensors. So alternatively, what the researcher done, they go for wearable sensor using MEMS microphone because it has high SNR and low power consumptions. So still there is some limitation in the wearable devices for auscultation purpose because it requires extensive time and labor to analyze huge data continuously collected by the clinicians. So now the researcher look into the recent powerful model based on deep neural network and recurrent neural network to predict the abnormal sounds, wheeze, crack, differentiate with the healthy sounds. And they got accuracy of 99%. But what is happening in the days, the researchers, what they done, they only classify the type of sounds, whether it is wheeze or crack or roach, but they not monitor the changes happen in symptoms or severity level of the patients. So now there is a need AI-based lung sound system which gained wide popularity in diagnosing various pulmonary diseases. So we already mentioned three prominent respiratory diseases are pulmonary disease, asthma, COPD, and pneumonia is the more prominent diseases. And we can use a AI-based smart stethoscope or machine learning algorithm to analyze the lung sound and provide a real-time feedback for precise diagnosis. This has happened. This is already done by researchers. So, AI-based system is evolved and is used as a diagnostics tool where there is a serious need and special care is required. So that's what this research has done. They developed this AI-based system. Over the years, this technology is evolved to diagnose a lung sound. So now we are going to see what our work is we are done. So we find out there is a various AI-based systems are available clinical. So and if you see if you want to like why this AI-based system is used, AI-based lung sound system, because reduce the human error as well as ease of remote and teleconsultants, as well as less healthcare visit and economical also. So that's why the system is now they move to the various AI-based system for diagnosing the respiratory pathologies like COPD, interstitial lung diseases, asthma, and pneumonia, tuberculosis, and more recently the earlier days like COVID-19. So these AI-based systems are more useful. And what challenges there in the real nowadays? One is the physiology of the lung sound origin. So there are different noises while oscillating with help of the electronic stethoscope. Different noises also recorded during oscillation that suppress the important features of the lung sounds, which results in the misdiagnosis. And most of the studies they implemented the conventional method. That is, one is short-time Fourier transform, wavelet transform, discrete wave transform, discrete Fourier transform for denoising the lung sounds. And another challenge is the reliability of the samples, online data sets. Most of the papers they use ICPH data sets for diagnosing or differentiating different sounds, lung sounds, and go for diagnosing a pulmonary disease. So the reliability of the samples from these web resources remains uninvestigated. Whether in what condition they recorded, those things should be taken care. That reliability of samples and statistical significance of the frequency domain signatures. So those things also should be done. Like if you're extracting some feature from the lung sounds, whether there is statistical significance or not. So that study should be done. And most recently, the features they extracted, time domain features, frequency domain features, MEL spectrogram features, and they apply some machine learning algorithm to differentiate the different lung sounds. So and they obtained the accuracy of 85.8%. and 95% and 98%. These are some accuracy they got it. And we want to find out, because the features can be extracted more time domain or frequency domain. But we want to apply some feature selection algorithm, and that is a one more challenging task. And we have to, as I mentioned, they use some online data set for training and testing validating better, but real recorded data sets which are limited. And we all know that the technology is evolving. AI models are keep on developing. So, and we know that the AI models it's a black box type model, and without any clarity, they are determined they're relating to the pathophysiology in pulmonary practice for improving the patient care. That is also one more. And what our work is, we aim to develop a intelligent based system based on lung sounds for diagnosing different pulmonary diseases. What is our objective is, we want to propose a standard protocol. Is it clear, sir?
Yes, yes. Go ahead,
Yes.
sir. No issues.
Yes. Okay, thank you. So to propose a standard protocol for lung sound data acquisition, and also we want to implement some denoising algorithm. As I mentioned, when you oscillate with the help of electronic stethoscope, there may be some additional noise also embedded with the lung sound. We want to cancel it. Most important interference is the heart sound interference, because those heart sound and the lung sound, heart sound frequency also within the range of lung sounds. So we want to suppress that heart sound, and we want to extract relevant significant features, because people are extracting features in time domain frequency. We want to extract some relevant feature for improving the diagnosis accuracy, and also with the help we are extracting the relevant feature, we want to apply some machine learning algorithm to classify the pulmonary diseases. So the solution what we are providing from our study, the most of the studies used online data sets, but what my scholar has went to Tanjore Medical Hospital and recorded that data in hospital, and with the help of standard protocol suggested by the doctors. And we apply some denoising method to cancel out the suppress the heart sound interference. And also for improving the accuracy, the feature which we are extracted is multifractal feature, which is extracted from the lung sounds. We are not extracted time domain or frequency features. We extracted multifractal features, and for training a model, whatever the recorded data, we use to train the model and to improve that accuracy. And also we apply some deep learning model on the available standard data by using two different features, septal and statistical features. These are solutions we are providing. So lung sound data acquisitions, this is a overall computerized lung sound framework for classifying the pulmonary diseases. And we all know that we use a stethoscope. This is now it is obsolete. 2 years before my scholars use this Littman 3200, and now the series is gone to 4200. So we use this electronic stethoscope for acquiring the raw lung sounds on different area, chest location area. And after collecting, we have the online data sets which is combined, and we use a pre-processing techniques, that is filtering the denoising methods, and we extracted the features and use the machine learning model to classify the pulmonary. This is the overall standard computerized lung sound based system framework. Everybody who's working on machine learning or computerized system, you want to make it. So this is a standard procedure. So our study participant, the 100 samples and male and female age range, and the samples contain different disease patients, asthma, COPD, pneumonia. 20 seconds sample recorded, 20 seconds duration of study 2 months, and spirometry test also is recorded because to validate, and also we obtained accurate 95%. So this is the experimental protocol for data acquisitions. We We know this oscillation points from the doctors, where and all you have to oscillate with the help of electronic stethoscope. This is the software is provided with the help of electronic stethoscope, where you can record the lung sounds, and those recorded lung sounds can be used for further processing. So the inclusion exclusion criteria, this is very important, because when you go for any clinical or biomedical studies, we need to have inclusion and exclusion criteria, and the studies, and also one more point is we need to have ethical clearance also. So we got ethical clearance from Tanjung Medical Hospital, and so in that we projected these are the inclusion criteria and exclusion criteria, and the recording procedure is very simple. We'll before getting explain the protocol and get the consent from the subjects and ask the subject for relax for 5 minutes. And then go for 2 phases of recording, like 20 seconds for tidal breathing and 10 seconds for breath hold. So the signal pre-processing, after recording the sounds, because as I already mentioned, heart sound interference is the most important one. We want to cancel out that heart sound interference. So we all know the different filtering techniques are available in the studies: linear filtering, blind separation, independent component analysis, modulation filtering, wavelet-based filtering, non-linear filtering, and what we used here, the first study what we go for is SG Golay filter, and then empirical mode decompositions and variable mode decomposition and enhanced variable mode decompositions. These are the denoising or filtering technique for suppressing the heart sound interference. So when you use a Golay filter, which is a low pass filter, and which similar to it's only for smoothing purpose, signal smoothing. It won't suppress the heart sound interference. That's what we find out. And if you see this original lung sounds, you have noisy, and then go for it, applying the Golay filter, which is a low pass filter. So you got only smoothing is done. So how this Golay filter is, because based on the filter performance is done by SNR value. So the SNR can be adjusted based on the order of the filter and the frame length. It's manually adjusted. So the limitation is we want the window size and the polynomial order. So that is very difficult to select. It's manually, we are trial and base, we are finding out the SNR rate. And and this study we done it for healthy subjects, and we propose that we find out we want to go for automate this Golay filter by using some optimization techniques, so that you can improve the performance of this particular Golay filter. And also we want to test this filter on healthy as well as abnormal subject also. Next, we move on to empirical mode decompositions, which is, we all know that it's a data-driven algorithm, where this decomposition method is simply you are splitting the complex data set into a simple monocomponent signal, where you call it as a intrinsic mode functions. So this method is adaptive and empirical nature, and it overcomes the limitation of short-time Fourier transform. The short-time Fourier transform is not adaptive in nature. So when you use empirical mode, it will overcome this limitation. And this is the flow chart how this intrinsic mode function is. You are splitting the complex data into monocomponent signal by iterative process. That's called you are getting intrinsic mode function. Based on the intrinsic mode function, we are reconstruct the original signal. So when you see this is a normal vesicular sound, is a normal sound. And you recorded the heart sound signal and mix the both heart and vesicular sound. Now you have this third sound is you have the noisy sound. So we apply this empirical mode decomposition, and this is what you will get to extract the intermediate mode functions. And after extracting intermediate mode functions, and you can see that how the power spectral density is there. Like you can see there is a overlap is there, mode mixing effect is there. And in which mode you can able to reconsider that original signal. That is very difficult. And if you see this diagram, noisy input is red color and the lung signal is, and reconsider signal, you are not able to reconsider the original signal. So because of this mode mixing effect and selection of the intermediate mode functions, it is very difficult, because the intermediate mode function is generated 11 intermediate mode function, which the selection of particular intermediate mode function is very difficult in order to properly reconstruct the original lung sound. And we go for variable mode decomposition. This is also adaptive method, and where you are getting a variable mode functions instead of intrinsic mode function. Here also variable mode functions. And what this VMD is useful. It is previous EMD and EMD has mode mixing problem, and as well as IMF mode function selection of mode function is difficult. But in VMD, overlapping of the mode effect is reduced, as well as we can select the modes also. But that is also trial and basis in the VMD technique also, the mode selections. But more robust in noise reduction. That is also advantage over the EMD and EMD. EMD is a ensemble empirical mode functions. So this is the flowchart for VMD algorithm. So where you can decompose the signal into different variable mode functions, and then using a Lagrangian functions, you can you can select the modes, like the different modes can be extracted, and then from that you can reconstruct with the help of mode composer. We can reconstruct the original signal. So you have the noisy lung sounds, which has the lung sound as the heart sound interference is there, and apply the VMD algorithm, and you can separate the heart sound with the help of mode composer. You can detect the heart peak detections and localizations, and remove the heart sound from the lung sound, and once again apply the mode composer and to reconstruct the original signal. And this VM mode composer will know that how many modes should be, the variable mode function should be generated. Based on the mode function K value, you can able to reconstruct the original signal. So, and this is the flow chart for a variable mode decompositions. As I mentioned, you are decomposing the complex signal into K number of modes. And it's an iterative process. So, as I mentioned, this is a equations. It's a basis functions, and with the help of Lagrangian functions, you can find out the K number of modes. Based on the K values, you can able to minimize. So first of all, what the procedure is, first initialization is done. You have to select the number of modes should be mentioned, and mode weight can be initialized, and repeat until it converts, and update the mode weights, that is AK value. For each mode K value, you are getting that, and update the mode vector also. Once it is converged, and check the mode weights is small, and otherwise it's continue the iteration process, and extract the VMF, variable mode functions. So the challenging task is here what we find out appropriate mode, that K value for decomposition. That is the challenging task. So now we want to, if you see this, the K value in variable mode decompositions, you can know that like frequency versus PSD. So here the mode, you have to give K values given by the, you have to input that K value so that number of modes can be generated. But here the mode mixing problem is not there in VMD. But one is the K value, we have to trial basis, we have to give that particular. That is the problem is there. Choosing the number of modes is very difficult. That is in VMD. And finally, when we in this study we find out we obtain low RMS value and mean absolute error also. So we want to go for improved version of this VMD techniques. That motivate that's how we can cancel the heart sound interference. That's in the next study we have done it, improvised version of variable mode decomposition. So this is the framework for enhanced version of variable mode decomposition. How this K value is selected with help of judgment index. So enhanced variable decomposition to remove the heart sound interference from the lung sounds, and it automatically determines the mode number, the K value for signal decompositions. So this K value depends on the judgment indices. One indices is normalized permutation value, extreme frequency domain value, Curtis index, energy loss coefficient, and dominant frequency spacing. These are the some judgment indices should automatically determine the mode number, that K value. So normalized permutation in entropy, which quantifies the complexity and random of the each modes. So if the threshold value is denoted as mu2 and it's set as 0.4, and if the noise is there, higher permutation entropy will be there because of noise and additional fluctuations. So the mu2 value we have to properly put up. And extreme frequency domain, that's another judgment index where the extreme points in the frequency domain of the efficient mode, that is N1. If N1 is 1, that the efficient mode, or 0, it is an noisy. That's in algorithm we have to. So mu3 is the mode mixing in the efficient mode returned to VMD. Then otherwise in a variable mode functions. And then Curtis index. It's indicated to identify the sudden drop in the amplitude near the dominant peak. So mu4, if Ki is greater than mu4, it's a noisy mode, or else it's absolute noise. Then another indices is energy loss coefficients, which is square root of the ratio of the energy of the decomposition residual to the energy of the original signal. So this is a flow chart, the enhanced version of the variational mode decompositions. So you can easily understand. First of all, you have to initialize the value of the weight as well as the K value, K minimum and K max, and run the VMD and find out the indices, apply the indices, judgment indices, and to get the appropriate K value, final K value for decomposition. So, excuse me, madam. Hello.
No, sir. I think someone is. I think someone is not mute.
Okay. No issue. Okay. What we we want to compare whatever the algorithm we proposing. We want to compare with the earlier algorithm.
Excuse me, sir. There is some question I think participant asked or something is there in the chat. If you take it right now, you can. Otherwise, we can discuss in the last. Your wish, sir.
We'll discuss in the last, sir.
Oh, sure, sir. Yeah, please go ahead. Yeah.
Yes,
thank you.
So whatever algorithm we are proposing, we want to validate with the existing algorithm, which is already there. So we done it EMD, ensemble empirical mode algorithm also we have tested, and this is the results what we obtained. And pure lung sound, and when you apply the EMD algorithm, how it is related to reconcile the original lung sounds. And complementary ensemble empirical mode decomposition algorithm also we applied, and single site analysis, single spectrum analysis also we have applied, and VMD algorithm also we applied. And this is the enhanced version of this, what I mentioned, the K value, how the mode is automatically selected. The 4 number of mode is variable mode function is done, and we got the reconstruct the original signals, how closely we are reconstruct the original signal, and we compare the all the algorithms. When you see all the figures, you can able to understand the enhanced mode variational mode decomposition reconstruct the original lung sound, very close to the original lung sounds. That's what we you can see all the graphs. Like one is EMD, ensemble empirical mode decomposition, complementary ensemble mode decomposition, single spectral analysis, variational mode decomposition, and enhanced variational mode decompositions. So we want to know, once you apply, we want to know what is the performance of the particular algorithm. So with the help of 4 parameters, root mean square, correlation coefficient factor, normalized mean absolute error, and signal to noise value. With the help of these parameters, we can analyze the performance of the particular algorithm. So we compared also, and we find out the high SNR 28.52 and low RMSE value, and the CPU usage time, how much time is required. Like you can see the CPU time is 0.4 and then 34. So this is the comparison of the performance metrics obtained by the denoising methods. What we are concluding from this study, the proposed algorithm implemented on the real-time data sets and to separate the heart sound from the lung sound without changing the original content of lung sound. And we achieved better performance metrics as compared to the other existing algorithms. And we obtained the RMSE of 0.02, high SNR of 28 point, minimum mean absolute error of 0.0009, and maximum correlation coefficient is 0.9, and low CPU usage, low CPU time. And this algorithm can be used as a pre-processing step in a lung sound analysis system to improve the diagnostic accuracy. And in order to obtain the best decomposition level, still the K value, which is we need to go for feature optimization technique can be implemented to get the optimal tuning parameter of the mode, the K value. Now the algorithms keep on evolving. Now the other algorithms are come up, but this is 1 year, 2 years before we have done it. So, and next is we want to apply a machine learning. Whatever the first pre-processing part is done, next we want to apply machine learning to classify the pulmonary disease through the lung sounds. And this is the architecture framework of your study. And we use the same electronic stethoscope to record the lung sounds. And we apply signal pre-processing and feature extractions. And the standard machine learning algorithm, which we implemented. And this study, as I mentioned, we recorded the lung sound from the patients in Tanjung Medical Hospital, and ethical clearance also obtained. So pre-processing, as I mentioned, here we used 2 stages of pre-processing steps. One is we apply variational mode decomposition, and we apply a discrete wavelet transform to further remove the noise. And we, when you apply the 2 stages, and we want to know the performance of the particular 2-stage algorithm, and we same 2 parameters are used. One is mean square error and the SNR. That's a performance parameter. And this is a VMD filtered signal. And once you we apply to the DWT, and we got this. So after DWT, what is a SNR value? So this is what we obtained. So it is improved, the SNR value, because the noises are removed. So the SNR value is removed after applying to the DWT. So we apply feature extractions after pre-processing 2 stages of pre-processing, and we apply feature extraction and evaluation process. So we all know that why the features are required, because we want to know the because the raw data is there, and we want to know some representation like features which is relevant for the diagnosis. So we apply some mostly they use a statistical analysis or a discrete Fourier transform, frequency domain analysis, time domain analysis to extract the features, or septal analysis to extract these 2 features, MEL frequency, gamma tone frequency, septal coefficients, or they apply wavelet transform to extract the wavelet coefficients and autoregressive model. These are some techniques to extract features from the raw data. And we know that time domain features, as I mentioned in the study, there are features, time domain features, frequency domain features, spectral features. This can be extracted from the lung sounds, and statistical features, and time frequency domain features. So feature extraction, as I mentioned, we are transforming the raw data into numerical features that can be processed by preserving the original information in the data. So in the lung sounds, it's a non-stationary in nature. We all know that. So the single feature alone cannot be useful. So extracting useful information from these lung sounds, which is useful to reduce the computation time of the classifier what we are using. So earlier studies, what they've done, they use some the wavelet transform technique to extract some wavelet packet energies and wavelet entropy features to classify healthy COPD and asthma. And recently, the 2 septal features are extracted for classification. One is MEL frequency spectral coefficients and gamma tone frequency spectral coefficient. Here, what we in our study, we extracted 13 MEL frequency spectral coefficient instead of extracting the wavelet features, and 13 gamma tone frequency spectral coefficients we are extracted. So total 26. And what is MEL frequency spectral coefficients? So we know the lung sounds, and with the help of DFT, discrete Fourier transform, by applying a discrete cosine transform, we extract the Bell frequency spectral coefficients. And this is the function. And gamma frequency spectral coefficients, how it is related, because this is useful in speech processing applications. But here, because that we know that in a human there is a cochleus there. It's a basal membrane where you will get the sound that whenever it vibrates, produces sounds, energy. So we related to the lung sounds. What we are when you are doing the this GFD is the function for this because we are mapping to the auditory map these sounds. So after extracting these 26 features, we apply to the machine learning algorithm and to classify the pulmonary disease. So the machine learning algorithm, we all know that the standard algorithm which is there in the paper, like in the literature, if we come across more prominent random forest, K neighbors neighbor, decision tree, linear discriminant analysis, most commonly used one. So so we take it this from the literature, we apply the same the 4 machine learning algorithms, and we obtain the confusion matrix. And to know the algorithm performance, we have the 4 parameter: accuracy, recall, precision, and F1 score. So from the confusion matrix, you can be able to calculate what is accuracy, recall, precision, and F1 score. And AUC or ROC curve, which is used to know the, if you go for a binary classification, you know the performance of the particular model. If it is right in the range of 0 to 1, then if the A value is great, between 0 to 1, and the AUC denotes that the model is performing better. So if you see this LDA, this linear discriminant analysis, K neighbors neighbor, and this is a decision tree and random forest. And when you see the performance comparisons, we, as I mentioned, the 4 parameter accuracy, recall, precision, F1 score. So this is a data online data set, ICPH 2007. It's an online data set, and a hospital collected. This is our own collected data set from the Tanjung Medical Hospitals. And we implemented all this algorithm. We find out random forest is performing. That is, if you see the accuracy level is 99.7. And also, if you see the precision is 97, and F1 score is also 100. So an average accuracy, like if you see the 97, as well as the macro average also 97. So this is the classifier results, and we also find out the performance timing, the training and testing timing also denoted here. And random forest, as I mentioned, from the table, we find out the accuracy is 99. Others are 100%. And from this, we know that while applying this machine learning algorithm, we come to know F1 score 100% and other recall, and because the model is overfitting, because the less number of data in COPD. If you see the number of recordings, if you see asthma has a higher recording, COPD is only 46, and other 44 and 28. So as it clearly says that accuracy is, but other things are 100%. You can't get 100%. But this is because of the model overfitting. And we test training 80% and 20% also, but the sample size is not equal. Asthma, COPD, and bronchitis and healthy. So the proposed machine learning system, what we have done, it classifies the pulmonary disease, and we apply some pre-processing techniques and get the high signal to noise ratio. And we extract the feature, 26 features feed it to the model, and we obtain the accuracy of 99.7 per random forest model. And in earlier studies, we want to compare with the earlier studies, they obtained a 99.3% only. So we got enhanced outcome, but still there is a data imbalance. And we are not applied any statistical significant feature analysis. So these can be taken care in the future work. That is what we proposed it. And ultimate aim is we want to develop a cost-effective portable system, a stethoscope for data acquisitions, and which can be taken as a future work. And for the rate of classifying the pulmonary lung sounds with the accuracy of 80.5%. The pulmonologist who is classifying the abnormal lung sounds only 80 point. We want to achieve more than that also. So now the clinicians are go to the AA analysis. So next study what we have done here. We want to propose a new feature. That is the approach for diagnosis pulmonary disease classification. That is multifractal, which is a feature. Because if you see the multifractal structure, which are almost in all biomedical signal, it's a time series one. And multifractal spectrum can be identified what is the deviation in the fractal structure within the time period, whether it is a large or small fluctuation. And we introduce this is already there in the other signal, biomedical signal analysis, what they applied this multifractal treatment fluctuation analysis. And we in lung sounds, we apply this multifractal treatment fluctuation analysis to estimate the multifractal spectrum. So we introduced this in the lung sound signal processing. So this is how the structure is there, block diagram, where, as I mentioned, we recorded the lung sound with the help of stethoscope, electron stethoscope, and we combine these data sets and pre-processing with the help of VMD. And then we apply this multifractal detrend fluctuation analysis to extract these multifractal features. That is spectrum. From that spectrum, we extract these 7 features, that H, delta A, peak, F minimum, F max, and then apply a standard algorithm, what is SVM, KNN, random forest, decision tree, Gaussian navigation bias, quadratic discriminant analysis to classify these 6 classes of diseases. One is asthma, COPD, pneumonia, bronchitis, health. So what is the algorithm? If you see this is a flowchart of this algorithm. We input this and we apply empirical mode decomposition for de-denting and divide the series into number of then you have to select the choice of Q value and analyze this, transform and obtain this. So if you see this, you are computing the mean of the time series data and integrate the profile of the fluctuated time series and split the integrated sequence into number of segments and compute the variance for this and computing the overall average using the logarithmic averaging method and determine the multifractal spectrum alpha and function of alpha and extracting the multifractal features from the multifractal spectrum. So the features can be extracted from the multifractal spectrum. So these are the, if you see the spectrum is look like this normal spectrum. If you see this spectrum A at the function of alpha, that is these are the features, 7 features which are extracted from this multifractal spectrum. First component and right extremity of singularity exponent alpha max, left extremity singularity exponent alpha minimum, multifractal spectral width, singularity exponent, singularity spectrums corresponding to the alpha max, singularity spectrums corresponding to the alpha minimum. These are 7 features which are extracted from this multifractal spectrum. So for a normal healthy, this is the spectrum will look like. For a disease subject, this is lung sound, the spectrum will be different. So I'll show this. In this slide, you can easily analyze this. Alpha versus function alpha. If you see this second graph down, you can see this multifractal spectrum, how like the black color line, which shows the normal lungs healthy subject, and other blue color line, which sees that COPD is dark blue, light blue is a bronchitis. So the spectrum is not look like a parabolic. So it's not symmetric. Only the normal disease, a normal subject have the spectrum is symmetric. But the other things are, one is left-tailed, other are right-tailed. So that's what is happening. If you see the plot, that multifractal spectrum plot, the second graph, the figure, the above figure shows that normal is black color is, if you see the order versus the Hurst component, you can see that there is a difference is there. Normal subject black color is the normal, other COPD is, it's not. The order is keep on the Hurst component versus the Q value. So the multifractal, as from this graph, what we inference, what we have done, the multifractal spectrum for various diseases of lung sound is not entirely symmetric. So we applied to the, after extracting the feature 7 feet from the multifractal spectrum, we applied to the model. And this is the ROC curve for the particular quadratic discriminant classifier model. And this is the confusion matrix. We take it as 6 classes diseases, or 4 class and 3 classes diseases. And these are the confusion matrix. And we evaluate this performance of this algorithm. And we taken a parameter accuracy, precision, specificity, and sensitivity F1 score. And these are the algorithm we implemented: decision tree, random forest, support vector machines, Gaussian neighbors, K neighbors neighbor, quadratic discriminant analysis. And in this, if you see this accuracy level, quadratic discriminant analysis perform better, 99.7 for a, and others are not performing, only 9. It's quadratic discriminant analysis performing better. So if you see that this classifier we apply to the TMC data set separately. This table shows that combined data set, online data set, we mixed with our recorded data set, and we separately analyze, apply the model to our recorded data set, and we find out same quadratic discriminant analysis giving better accuracy. And we apply this model on the multimedia respiratory. There is another data set. As I mentioned, ICBH one data online data set. Another multimedia respiratory data is another online data set. In that also we extracted the multifractal features, and we see this how the COPD severity level is, the spectrum is arranged. This is not a symmetric, and this is a disease subject COPD, and the COPD we have different severity level. Under risk, you see that under risk, it is showing that the spectrum is like this. And if you go, it's a right-tailed. So this is not symmetric. So from this multifractal spectrum also, you can able to differentiate the severity level of the COPD diseases. And we apply this on the particular data set. We apply the same algorithm, and we obtained a random forest is performing better in this on the multimedia respiratory data sets. So we proposed a multi-treatment fluctuation analysis to extract the multifractal features for and employ the machine learning for classifying the 6 classes of disease. And what we have proposed here, it's a multifractal features, and we got accuracy of 99.7 by applying a quadratic discriminant classifier model. So this innovative features can be enhance the diagnostic accuracy also. So further, what we are planning, we want to improve this because, as I mentioned, time domain features are there, frequency domain features are there, and this also one more feature, multifractal features are. Then we want to apply some feature selection technique and fine tune the training process also. And finally, I'm going to close it. We are applied this deep learning algorithm for classifying the pulmonary disease, and this we have done it earlier. When you start this study, we download this ICBH dataset and we apply this deep learning algorithm. And it's a subject independent model where you can diagnose pulmonary disease. So here we have extracted MEL frequency spectral coefficient only. It's a MEL frequency spectral feature driven subject independent model to classify chronic and non-chronic pulmonary disease. If you see, there are 6 diseases are there, pulmonary disease, and we split it into, we want to classify as a chronic and non-chronic pulmonary disease. So this is ICBS datasets, 2017 dataset. These are the details, how many hours of sounds are recorded and what frequency range, sample rate they use, and how many seconds they recorded, how many subjects, and 37 files are pneumonia and 16 files, 793 files are COPD. These details are there when you download this dataset, ICPH 2017 datasets, and patient's ID is there. And it's a subject independent model what we have done. So same noise filtering, they apply 50 to like the frequency range of lung sounds is 50 Hertz to 2500 Hertz. So they apply 6th order. Basically, before starting this, all the other features what we extracted before that, we we download this data, we directly apply this deep learning model. That is, so we use a standard 6th order Butterworth filter for removing the noise. And data augmentation technique to increase the sample size, we apply some data augmentation techniques. And we extract the features. That feature is called Mel frequency spectral coefficients. A feature is extracted and convert that feature coefficients into spectrogram, Mel frequency spectrogram. Because for deep learning model, we have to apply spectrogram image to the model. So Mel frequency spectral coefficient, how it is extracted. This is the flow chart. This is the steps to obtain the Mel frequency spectral coefficients. And this is the Mel frequency spectrogram image. So this can be fed into the deep learning CNN model, convolution neural network model. And this is the convolution neural network structure. And we use the activation function of Rayleigh activation function, which is the most commonly used activation functions. And same training 80% and 20%. What we obtain training accuracy of 97, testing accuracy of 86.25. So and this is the model accuracy, and this is the model loss graph. And what we find out, this testing accuracy can be improved. If you go for a higher, like other models, like combining two hybrid model, this testing accuracy can be improved. That's what we find out. And this is a confusion matrix, and this is a classification performance, a chronic, non-chronic, and healthy. And what we obtained is accuracy of 89. And the earliest studies, what the standard 2 years before, how the other papers, what they done, the standard model, they use it, and they got obtained a 65%. And when we are proposing the Mel frequency spectral coefficient features based on CNN classifier, we obtain 89.15 accuracy. So after this, now more number of studies are done in the deep learning system. Hybrid models are come up. So those can be implemented on the real time. Instead of applying on the ICBS data set, we want to go for our own data sets. So the outcome of my whole talk is what we like my scholars research is, we want to develop a non-invasive, cost-effective procedure to efficiently diagnose the pulmonary diseases. And the procedure should be fast enough and convenient than the conventional spirometer. Because if you use a spirometer technique, the patient effort is required. Also, error will happen when you go for a aged subject, the air leakage will be there. And we can't use a frequent exposure of X-ray techniques to correctly diagnose the pulmonary disease, or we can't go for a high costly technique, CT. So we want to give a screening tool instead of using a conventional spirometer. And also noise reductions with the help of advanced filtering technique can be applied. A relevant feature can be extracted, and feature selection algorithm can be applied. And so we want to no quality feedback from the patient is not required. Like ask the patient to relax mode, and we obtain the record lung sound and know whether they have the COPD or asthma. So intelligent-based system is a reliable clinical lead, as from our study we find out for early diagnosis of the pulmonary disease. In future, we want to implement some low-cost, high-reliable digital stethoscope we want to develop. For example, if you see the commercial diaphragm which is there in electronic stethoscope can be replaced with a 3D printed material also. For signal transmissions, the lung sound signal can be transmitted via Zigbee, or we can go for some IoT or IMOT. And further, the wearable device can be useful in all weather conditions also. So basically, you want to develop an intelligent digital stethoscope to improve the diagnosis. Regarding if you go for intelligent digital stethoscope, the battery processor and embedded algorithm, those can be we have to take care. And this is the recent work which is happening in this pulmonary diagnosis, digital pulmonologist field, where they use this microwave imaging system And we all know that microwave means its range is 0.5 gigahertz to 9 gigahertz. So this is used in image to know the tissue abnormalities. So this is safe diagnosis tool which can generate the image based on the difference in the dielectric properties. So this is mostly in breast cancer, bone tumors, stroke, pneumonia, lung cancer part. This microwave imaging technique is used. And basically, this is a diagnostic method for can be applied on lung pathology also. If you go for a clinical application for pulmonary disease diagnosis, you want to design an improved antenna version, hardware design should be done. Previously, what the study has done, they use some microwave acoustic sensor applications, which is used in a power plant, aerospace, and defense. And this microwave can be used in other research also, last few decades. So what we, this is a system which is there, AI-assisted microwave-based dual sensor system for digital pulmonologies. It's a novel system where they use acoustic PPG sensor and they use some intelligent array of microwave antennas. And which is this system can provide a novel biomarker for assessing the various lung pathologies. So here also they use some AI techniques. So in future, what they need to be done, they go for some micro hardware designs. Like that's the ultimate improve the antenna and the hardware part, properly diagnose the lung diseases, and improve the telemetry part also, noise-free transmissions. So now we move on to digital pulmonology, means digital era is moving. We are in the era of digital health. So we want to go for employing a novel AI-assisted microwave tools. So this is a study which has happened in the earlier days, like in IIC Bangalore. There is a lab called Spire Lab, where they develop a system, capture this breath sound from the mouth and chest, and apply some data-driven algorithm to calculate the pulmonary function test variables. Because instead of using a spirometry, they want the same parameter how we can extract with the help of breath sound itself. This is a system that they called as a phonophore. This system integrates this microphone in two different forms. One is record the breath signal and simultaneously listen the earpiece sounds also. In order to minimize because the external interference we want to minimize. Also in spirometry, as I mentioned, there is a sound leakage is also there. To minimize this, they developed this phonophone project. And there is another study which is AI-based algorithm, which is for a neonatal baby. They want to diagnose asthma. How this can be applied? Like they use this wearable stethoscope, which is to monitor or record the wheeze sounds, and then diagnose whether they have the asthma. That's called the LSMP sensors. And this is the research is happening, like how we can record this in a neonatal baby. So the overall era is we are in the smart stethoscope, that's a digital era. So if we see the practice, what is happening in the clinic, we are in the stage of, you see that this is the last slide of this. We all know that we developing this electronic stethoscope. We record this data and we are applying AI analyzer, we are applying. And then we are going to develop some processor and we move on to wearable. And what we expected is this can be used in the home care as well as in isolation ward as well as in telemedicine. And remotely we can monitor. But what we are here, this is now we are developing. This is the stage where we are. This green color is there where we are developing. And we developed this electronic stethoscope is already done. The record how with the help of the electronic stethoscope improvement is done. And where we are here is we are now move on to AI-based analyzer and wearable stethoscope. And what we expected from our researchers' point of view, this whatever we are developing, it can be used as a home care system also, or in an isolation ward, or in a remotely monitoring like that. So this is the final takeaway from my talk. So we all know that the institutional ethics board, I don't know, people are working on biomedical. Everybody should know this, how the ethical board, how members are there. So this is the member size, and this is a committee, how it is they evaluating this biomedical related project or clinical related projects. And these are the flows, how they are evaluating, how the inclusion criteria. Thank you for patient listening.
Thank you, Dr. Periyasamy, for your insight regarding the diagnosis for pulmonology. So it's a great insight, sir. Thanks for your valuable time and all. So from the participants, do you have any query or any question? Please raise your question. So Dr. Periyasamy with us, so he will help us to understand the things more deeply. From the participant side,
Sir, good
do you
evening,
have?
sir.
Yeah.
Good evening,
Yeah.
sir.
Yes, sir. Good evening,
Sir,
sir.
I am Dr. Bharani Srinivasan. Dr. Bharani Srinivasan from Puducherry, sir.
Yes, sir.
Rajiv Gandhi College of Engineering and Technology, Department of Biomedical Engineering.
Yes, sir.
Sir,
Good
your
evening, sir.
presentation is very nice, sir. Thank you. Because too many works we are also doing with this. So,
Yes, sir.
what is the things? The classification, shall we have each classification of the? This is how many size of the stones, sir? That because we are getting that the sample getting for trained and trained is very difficult. So each time different classification of the disease are there. So how could we get it this way?
Because we, when you use for any machine learning model, we are for training, 80% of data is training and 20% for a testing purpose. And for improving the sample size, you can go for data augmentation techniques or some other techniques also available to improve the data imbalance. That is the one limitation of my whole research. If you see the sample size is not equal, the data imbalance is there, and we are not applying any features.
That's why I'm asking. Each classification having different samples, we may get it. So
Yes.
We may not be get as a balanced data.
Yes, sir. Now the techniques are available, sir, for balancing the data imbalance can be minimized. There are different techniques are available that can be applied to minimize the data imbalance. And also, when you go for feature extraction, what feature can be? You can't extract all the features like as I mentioned, time domain, frequency domain, time frequency domain.
Yes, sir,
this cannot be extracted all the time. We want apply some feature selection algorithm. And from that, we can know that which is the relevant features for diagnosing purpose. So the feature selection algorithm, people are working on like it's already happening. So that is another part. And third part is every time we are applying machine learning algorithm, which is a well-known algorithm already available, people are already developed and implementing on the data. But we need to go for some hybrid model instead of using a well-known standard. As we see in my slide, the standalone machine learning algorithm which I applied, but still we need to hybrid that model. Hybrid model we need to apply. Fusing should be done. Fusion of algorithms should be done in order to improve the accuracy.
Okay. Sir, again, sir, sorry. Sir, one more. What about the accuracy of manual diagnosis with this machine learning and in your work? Have you done manually with these data for the particular patient?
Yes.
If a sample of one patient you have taken, you can train with other thing, we can get the result. So you have gotten some predicted, some interpreted results. That have you compared with the physician?
Yes, sir. Because as I mentioned in the first slide, the standard protocol which we used, when you go to the hospital, my scholar is done like the doctor who is referring that patient, we know that spirometric test is already done for that particular patients. And after that only he is referring this patient is having asthma or COPD problem is there. Now you can, there is next to the clinician, there is a room is there. When the doctor is referring that patient, and that patient will come to the particular room and be recording that this lung sounds.
Okay, so lung sound. Thank you, sir. Thank you, sir. Your nice explanation, which is helpful for us in future research with us. Thank you, sir.
Yes, sir.
Thank you, sir.
Yes, sir.
Yeah, thanks, sir. Sir, there is some questions in the chat. Do you need more time, or how it's handled? Like from the
I'm just reading that question only.
Okay.
As I mentioned, one Dr. SSK, sir has mentioned spirometer help diagnose condition like asthma, chronic, and bronchitis by measuring the lung capacity and airflow. That is true. That is, the spirometer is the standard, well known. This lung sounds people are not accepting. In as we go to the doctor in when you go for ethical clearance, we also struggle to convince the ethical board. When you're proposing a new tool to diagnose these conditions, asthma, chronic, and bronchitis, people will question, we have already a spirometer. Why you want to apply this new tool? In the same ethical board also, they question us. They are not allowing this lung sound recording and all. And finally, we convinced us, as a academician, as a researcher, we want to propose, we are not replacing the spirometer. We want to go for lung sound as a pre-screening tool. That is the only thing we have proposed. And it's also non-invasive. We are not injecting anything. We are not asked the patient to more forcefully expire the air, or in spirometry, the test is, if you want to record the pulmonary functions test, the force expiratory volume level we need to extract. So for that, we ask the patient to forcefully expire the air. So sometimes the air leakage will be there. So to avoid that, anyway, that spirometer is a standard state-of-art technology that we are not questioning. But what is the error is happening? That is the air leakage problem. That we want to address it. So whether we can address with the help of small auscultation technique, that's what we are doing. That is the first question answer. I'm not questioning this spirometry part. This is well known. This is a clinically accepted technique which is used in the hospital. Still this lung sound is not in the under research level only. Everybody, if you see all over the hospitals, people only use the spirometry.
Okay.
And which uses the artificial intelligence to allow patient to test their lung function at home. Yeah, this is not, as I mentioned, this is only research level. As I mentioned in the last slide, if you want to go for useful in the home assisted, we are not in the stage expected outcome. What in the last slide which I mentioned, we are still in the developing part. The AI is evolved. Now we want to make a processor, and then the expected outcome is we want to use it in the home care as a home care device. So that still we are not into that particular point. If you see my last slide. And then another sir has mentioned, SSK sir has mentioned, totally wrong. You can get the spirometer with the, I agree with that point, Dr. SSK sir. The spirometer parameter is a important thing to know, because to validate anything you are proposing, you want to compare with the standalone system which is already used in the hospital. That is a spirometry system. So that is already happening in the hospital. Like clinician is referring that patient, you record the spirometry data as well as record the lung sound. We want to get to know the relation between the lung sound and the spirometry relations. So that spirometry data as a feature also we done study when I'm in the NIT Raipur. There is one of my student has done. That feature also taken into consideration in modeling, machine learning model. Instead of lung sound features, the spirometry feature also integrated into this model, and we got accuracy. That paper also, that is one of my scholars done, Nishi, when I'm in the NIT Raipur.
Sir. Actually, it's out of time. Like so, 7:30. So our next section will start at 7:30. So it's a nice time, sir. So in the
Yes, sir.
participants also, like if you have any extra more queries or anything you need to clarify, you can. I think you can contact him directly. So thanks, sir. Shelly, ma'am, do you need to
Thank
add
you, madam.
anything?
Thank you, sir.
Shelly.
Thank you, sir. Thank you very much. Sorry, sir.
Yeah,
Actually, sir,
Vaithiyanathan,
there will be some problem in my net, actually.
No issues,
okay.
sir. No issues.
Yeah.
Thank you.
Thank
Thank
you.
you very much.
Vaithiyanathan,
I'll
yeah.
keep in
Thanks.
touch with you, sir. Keep in touch
Thank
with
you,
you,
sir.
sir. Thanks, sir. Thanks a lot, sir.
Thank you. In NIT
Take care.
Delhi also, people are working on this. I have seen recently one paper is.
Yes, sir. Dr. Sandeep
I
Kumar,
said-
or who is that, sir? Dr. Sandeep Kumar?
Yes, a recent study. I am looking into whatever the work is going on in this lung sound part. NIT
Okay.
people also doing.
Actually, in our
So-
department, Dr. Sandeep Kumar is working on signal processing more, and that is medical image processing and signal processing is more interested. He's working.
Okay.
I don't know who's your pinpoint. You don't know, but in our department, he is working on that area.
Okay.
Okay, sir. Thanks, sir. Good
Thanks,
time,
sir.
and thank you, sir. Thanks a lot.
Thank
sir.
you, sir. Thanks for inviting me, sir. Thank you, sir.
Thank you, sir. Take care, sir.
See you, sir.
Thank you.